Hello everyone and welcome to Math Made Easy and welcome back to the complete course of the numerical analysis. In the previous lecture, we discussed the importance of numerical analysis and why approximate methods are required. Today, we begin one of the most important chapters of numerical analysis, the error analysis. Whenever we solve a problem numerically, we rarely obtain the exact answer. Instead, we obtain an approximation. So naturally, the first question that arises is how close is our approximation to the exact solution? And to answer this, we study errors. Suppose I ask you to write the value for pi. Some student may write it as 3.14, some may write it as 3.1416, or some may even write as 3.14159265. Then ask which one is correct. Actually, all of them are approximations because the decimal expansion of pi never ends. Therefore, the difference between the exact one and the approximate one is known as error. And the true mathematical value is typically known as the exact value, and a value close to the exact value is the approximate one. In practical computation, especially on computers, we usually work with the approximate values because storing infinitely many decimal places is impossible. Now, the question is, why do errors occur? There are several of reasons. Firstly, many mathematical numbers such as this pi, this root 2 and this e have infinitely many decimal places. Secondly, computers having the limited memory. They can't store infinitely many digits. Thirdly, the numerical methods. They are themselves are approximation techniques. And so instead of finding the exact answer directly, they gradually approach the solution. Therefore, errors are unavoidable in numerical analysis. So remember the statement like we can't completely eliminate errors. Our goal is just to minimize them. As whenever we solve a mathematical problem, numerically we usually obtain an approximation rather than the exact answer. Therefore, understanding errors become essential because it helps us to judge the quality and reliability of our numerical solution. Errors can be understood from two different perspectives. The first one is where did the error come from? In other words, what's the cause of the error? And that gives us the sources of errors. And the second one is how large is the error? Once an error has occurred, we need a way to measure it. And this gives us the measure of error. This distinction is extremely important. See, one tells us why the error occurred and that tells us how much error is present here. So the first source is inherent source. It's also known as to be the data error. And these error already existed in the data before any computation begins. They usually arise due to the limitations in measurements, instruments, or in experimental observations. For example, if I take a rod and having the exact length is 25.42 centimeters, but the measured one will be 25.4 centimeters. Then the error already exists in the measured data. Even if we use a perfect numerical method, this initial error can't be completely removed because it is present in the input itself. Then comes this round of error. The second source is round of error. Computers and calculators can't store infinitely many decimal places, therefore numbers are rounded to a fixed number of digits. For example, if I write the value for the pi, which is approximately 3.1415926535, but a calculator may store only 3.142. And this small difference introduced due to rounding is known as the round of error. And almost every numerical computation performed on a computer contains some amount of round of error. And the third source is this truncation error. And unlike the round of error, truncation error doesn't arise because of limited computer memory. It arises because we intentionally replace an infinite mathematical process with a finite approximation. For example, if I take the Taylor series of e to the power x that contains infinitely many terms, as this e to the power x equals to 1 plus x square by 2 factorial plus x cube by 3 factorial plus x to the power 4 by 4 factorial and to so on. Suppose we approximate it as e to the power x equals to 1 plus x square by 2 factorial. The neglected higher order terms are these that produces the truncation error. And whenever we ignore remaining terms of an infinite series, we introduce the truncation error. In practical computations, we often keep only the first few terms and ignore the remaining terms. And mostly the numerical methods rely on approximations. So truncation error is one of the most common types of error in numerical analysis. Once an error has occurred, we need to measure it. And numerical analysis basically uses 3 standard measures as these. First one is the absolute error. The first measure is absolute error. It is simply the absolute difference between the exact value and the approximate one. Basically, the mod value of the true value minus the approximate value. It tells us the magnitude of the error without considering the size of the original quantity. For example, if I take the true value as 5.678 and the approximate value as 5.670, the absolute error becomes this 0.008. So the absolute error tells us here the magnitude of the error, but it doesn't tell us whether the error is large as compared to the actual value. Now comes the relative error. Instead of looking only at the difference, relative error compares the error with the true value by this particular formula. And this gives us a better indication of how significant the error actually is. For example, if I take the true value as 20 and taking the approximate value as 19.8, then this absolute error is already 0.2. Then the relative error becomes this 0.01. The relative error tells us here the size of the error relative to the actual quantity. Now comes the percentage error. Finally, we have the percentage error, which is simply the relative error multiplied by 100. So expressing the error as a percentage makes it much easier to interpret and compare different approximations. Basically, you have the relative error as 0.01 and the percentage error becomes this 0.01 multiplied by 100%. That gives you 1%. So percentage error is commonly used because percentages are easier to understand and every numerical computations introduces some amount of error. So we first identify where the error comes from, and by studying the sources of error, then we measure the size of that error. And that brings us to the end of today's lecture. In this session, we learned what errors are and why they occur and how to measure them. We also introduced some round of error and this truncation error, these 2 important sources of error in numerical computation. And in the next lecture, we will continue this chapter by studying these significant digits, accuracy, what about precision, and this propagation of errors with detailed example. If you found this lecture helpful, consider subscribing to Mathemate and continue with the next lecture in the playlist. Until then, keep learning, keep questioning, and remember, every great solution begins with a clear concept. This is Mathemate. Thank you so much, and I'll see you in the next lecture.